And I will introduce you now Leif, Nissen, from XAIN. Make it up for Leif. Of course. The clicker is there.
All right. Hello, everybody. I'll present to you basically. Oh, what's that? Sorry. Didn't do anything. No? Okay. I'll present to you today blockchain technology and basically blockchain intelligence framework as a means to combine artificial intelligence algorithms with blockchain technology. My name is Leif Lundbeck. I'm the CEO of XAIN and also cryptographer at the University of Oxford and the Imperial College London. And this is my colleague Felix Reichel.
Yeah, hello. My name is Felix Reichel and I'm the head of marketing of XAIN. But first, what is XAIN? XAIN is originally originated in a cross-industry and science development project to leverage the real-time quality analysis and auditing directly on machine level through blockchain technology and also machine learning. Yes. To be closer to our industrial partners and also clients, mostly in the automotive but also in the banking sector, we are now seated in the Berlin Aerospace Technology Center. Yet parts of us are also located in London. Well, before coming to our Sorry. Okay, then we will switch. Okay. Before coming to our actual blockchain intelligence framework, I give a quick overview of our cooperation and our technical concepts. We developed the first mixed integer nonlinear programming simulator as the basis of all our developments and applications. It can handle hash range numerics to optimize for security, availability, and thus resilience within a certain budget in a corporate setting. It allows not only to permission, but also to govern our blockchain, which is also registered as a patent. The simulator supports then our actual product on protocol level and is as such only a part of our system. We developed two main applications. First of all, one for real-time quality analysis in industrial production and the other in auditing. Hereby we combine machine learning and blockchain technology to achieve what we call blockchain intelligence. Therefore, we developed an alternative new mining algorithm for a resilient data consensus. This mining algorithm or technology enables data analytics and also auditing of fast amounts for streaming data directly on machine or server level. This technology has been developed within 3 years of a cross-industry and science development project between the UK and Germany. All developments are based on projects, first of all with Imperial College in London, mostly for consensus algorithms, and the University of Oxford, focusing on actual machine learning algorithms adapted towards blockchain and also machine learning. Yes, now I give a quick overview or a high-level impression of our framework and its capability to solve imminent problems. Problems that blockchain solves in general and some that our framework solves specifically. Yeah. Nowadays, industrial production is increasingly influenced by terms such as big data or Industry 4.0. The need to analyze massive amounts of data in a secure and at the same time cost-effective way comes to its limits with common database architectures. Despite of using redundant hardware, the administration and also the monitoring suffers from a single point of failure. As we all know, blockchain can serve as a solution to solve the problem of a single administration and also of the problem of the single point of failure. Coming more specifically to our blockchain intelligence framework, we run our machine learning-based optimizer within the actual protocol to govern its functionality in a consensus. So this protocol is an alternative to PBFT and is based on completely dynamically mining algorithms. So let's.
First of all, I mean, blockchain technology in general solves the problem of mutable data. Because, of course, in normal database systems, you can, in retrospective, change data, and this makes it possible, for example, to really automate auditing, for example. And therefore, you do auditing basically by manual sampling. But in a blockchain system, generally, I mean, if you have, for example, an open blockchain system, first of all, you can basically secure the system, and you can prove, basically, that none of the data has been changed previously, and you can history-based link those transactions. And transactions don't always mean monetary transactions, but also just pure data transactions, for example, between single or several IoT objects. But our framework specifically is for the purpose of highly sensible data, for example, in an enterprise solution. Usually, I mean, if you basically put a blockchain system in an enterprise solution, people ask why to do that. I mean, there are even questions like, why don't you do like Google Drive or so? But of course, here, I mean, there's really the focus on highly sensible data and to prove that none of the data has been changed, and you have the easy tracking possibility, for example. And but then, of course, if you do all these things, for example, in an industrial solution or in a production solution or Car2X infrastructure solution, you may not always want to use open systems because you rely, for example, on prices or on the stability of the system. But then if you put the system, for example, in an enterprise solution, then you also need to make this system very stable. You need to handle high data throughputs. And of course, you need to handle insider attacks. And this is a huge problem. And therefore, you have, for example, as Felix also mentioned, the alternative of PBFT. But we also had a scientific test there where we attacked basically PBFT systems or proof of stake systems, and they basically break down quite easily. So, for example, if you have high incentives, as in industrial production, for example, but also in healthcare or financial institutions, proof of stake systems or PBFT systems may not always work. So we developed a new framework, which is based originally on proof of work, but to stabilize the system, we use, for example, Bayesian networks, but also neural networks to, for example, detect attacks, or to stabilize also the blockchain as such. And also, with our largest client, Mercedes, we have, for example, testing times that we need to consider. And of course, the system gets quite large. And if you have, for example, then miners breaking down or nodes breaking down, those testing times may vary. So therefore, you need to stabilize the system by detecting those things and reacting. Yeah, so but we also have a great advantage of being able to use smart contracts, which are basically small deployable programs, but I mean, they may not be always small, but they're just basically runnable programs which run on a consensus between several nodes. And on these smart contracts, you can also establish, for example, learning models which run on a consensus then on the nodes, and you can check and verify that these learning models do exactly the same as they are meant to be doing. So if you consider a normal corporate production framework, so you have, for example, factories, and you have machines in those factories, and you produce parts, and those parts are delivered between different machines, and those machines can be considered as IoT objects. And then you produce, for example, cars, and these cars may also want to communicate for example, optimizing the traffic. You certainly need data to be available. to analyze data, for example, to increase production quality. You need this data to be util. You need to basically scale your systems. And therefore you have different redundant database systems, and these database systems have, of course, different purposes. But as such, you need certainly to manage those database systems in order to do all those tasks, and of course to improve doing those targets. And yeah, of course you need to have your data secured. You need to integrate your data, which is of course a highly costly target and a highly costly thing to do. And of course this database management system always has the problem of being a single point of failure, and you need to amend this. Further, you have, of course, the problem that you can't always trust your data. Trusting your data is quite important, for example, for controlling purposes, but also for external requirements, such as auditing, which is then done by external parties in a manual sampling fashion, which is fairly inefficient. And then Car2X infrastructure is also, in that sense, quite a problem, because you can't always verify different IoT objects or even cars. And of course you have the requirement internally but also externally to trace all your products, for example if you do callback. So as such, blockchain technology is not there to basically replace all these targets, or to replace basically database management systems and do all these targets by its own. It's there basically to support database management systems and to reduce its overhead. And herefore, you have, of course, certain advantages that you usually achieve with a blockchain system. So you have a higher data availability, you have, or you don't really need to integrate your data and clean your data always. So, and then, of course, every program you do, or your program, is based on security by design. So you have data security as a basic layer, and on top of that, you build your applications. And, well, of course, tracing products is also a key task of blockchain systems because of the history-based linkage. And, also one of the key tasks is really to improve your auditing. You have a trusted infrastructure, you can prove that none of the transactions have changed, and you can basically automate your audits. This is, more, we more do this basically in the US market, because there you always also have a legal strength to do this, and Germany, it's a bit behind in that market, but internally these methods are quite efficient. And of course you can verify Car2X infrastructure. And you can also, for example, have different blockchains in your corporation that communicate to each other, for example, via sidechains. So one use case is just a small one, basically, that you have certain quality measures through high precision lasers during the real production, and you can also, for example, compute a real forecast in real time based on these IoT objects and communicate between these IoT objects, and can verify that these computations are actually true. And therefore, we have, of course, the aim to save energy, time, and material. But of course, not all of these computations are actually done in the blockchain. They are also done besides the blockchain, and then you have oracles communicating to the blockchain as such. So by blockchain intelligence, what we achieved is, so first of all, what we want to have is the full control, but control is not really meaning that people control it, but we have full control of a self-learning system within a corporation that is also self-optimizing as a network. So if you have changing circumstances, the network as such is also optimizing according to these circumstances. And of course you have a seamless integration into your normal database systems. You don't need to worry about that. And the blockchain intelligence framework as such is just an alternative to PBFT. In many applications, PBFT actually makes much more sense. So you have, for example, BigChainDB, which has quite a scalable system. But the problem is really, if you have high incentives of changing data, PBFT schemes break down quite easily and are not as stable. So therefore, in certain circumstances, we implement this system rather than PBFT systems. And also, of course, you have the support for automated audits and transaction tracings. And you can do predictive analytics or directly on DApps. And of course, you have the gain of security by competitions through the mining and basically the server race. So just as 3 proof of concepts to introduce you. So we have a first project with Mercedes-Benz, but also since yesterday we start with Porsche for such a proof of concept to develop, for example, in Cloud-X infrastructure, but this is a different topic. And herefore we have what we want to do is really to introduce real-time production tracking and also analysis, and this is done in the Mercedes factory in Marienfelde. And here, first of all, of course, we have the seamless integration into the normal database systems. And the problem that they have is that they have quite an old infrastructure, and they can't always change all their parts in their infrastructure. But what they have is really this database management system, which can fail. And if that fails, production stops, which is quite costly. So what we have here is really an alternative system which runs in parallel to the normal system to handle also the normal production data throughput in a consensus directly on machines. So even if machines are not online, you can still handle it, for example, through other networks which communicate with a blockchain network. And for that, what you want to achieve really is also this aim of real-time quality analysis. Of course, what we currently achieve is rather near real-time analysis because the network as such is still on the design, and we just do this for one production line first. And of course, you have immutable data, and this is also Mercedes quite a huge factor because they need to prove to legal providers, or legal participants, for example, that none of their data has been changed. And they need to provide this. And, well, in recent times, also lots of their data has been changed after the Volkswagen scandal. Then we, of course, can handle, of course, security management. We have security by design as such. Yeah. So the next proof of concept was actually our first project together with Credit Suisse. And here we have a huge problem of incentives, actually. So in the US market, you of course have mortgages, and these mortgages all have a certain risk level. And these parties need to, or the Credit Suisse actually wants to bundle these mortgages in mortgage bundles and then sell them on the capital market. But to be able to do this and to actually rate these mortgage bundles, they need to insure them by an external insurer, for example, AIG. AIG, however, can't trust the data of the bank, and the bank itself also can't trust their own data. So this is because individual bankers have a high incentive to actually cheat on the system to receive higher bonuses. And therefore they change data in retrospective of individual risk levels, and therefore neither the bank knows the exact risk level nor the insurer. However, with the blockchain system running in parallel to the normal database system, database systems are much easier to actually handle because sometimes you actually also need to change data. But every data that is handled in the database is also going as checksums into the blockchain system, and therefore you can also automate audits, and you can verify that transactions have not changed, and monetary transactions usually shouldn't change. But there are still cases, and these cases can, for example, be red flagged and further looked at manual auditing, for example. And then the next level is to have real-time quality analysis also on this frame. So you analyze the quality of these risk levels and also detect in which departments, for example, it's highly likely that such cases happen. And so actually we have a win-win situation because bankers can't really cheat on this system, or I detect it. The insurer knows exactly which risk level they are in. The bank also knows which risk level it is in, and actually also saves money because the insurer can now be sure on this risk level and lowers the premium. The next proof of concept, or the third proof of concept, really is actually the history of this system is now 4 years old. It was started by Cisco, and we partner also with Cisco now, and Imperial College London and the UCL, which is funded by Petros. And therefore we have in London, a part of London called London White City, where we have also IoT objects installed in traffic lights, for example. But we also have, there are certain partners like Jaguar there, which install those communication objects in their cars to test the system. However, the system works perfectly fine. However, it is easily attackable. So one attack, for example, was that a supermarket chain just inserted virtual cars on one road to guide the traffic exactly to their stores. And, well, this is, suboptimal in that sense. And also the police was actually attacking the system by inserting virtual police cars on certain roads. So people got the information to drive slower, for example. So, those analysis themes actually really rely on the actual verification that you actually know that there is this IoT object exactly on the position that it's meant to be, and that cars cannot double spend basically transactions of themselves. So a double spending attack is something that you can really prevent with a blockchain system, and you can verify all the transactions. And herefore we gain actually a much higher level of trust, which is then also built into the new G5 network, which is developed at the University of Zurich. Yeah, so thank you very much for your attention, and yeah, please to raise questions if you feel.
Anybody has a question? Or
Yes. Please.
One thing is consensus, so also when you say yes, proof of work needed, or your machine learning is proof of work needed, when consensus needs time, how are you solving this when you have like latencies in a second? And then
Yeah.
Sensors, or like the other topic, a robot, or quickly needs to adapt something.
Yeah.
It's data from blockchain, and this needs already to be agreed on, right? How do you solve this? How do you have something like master nodes, or
No, this is actually, we actually have proof of work, so it's an adaptive, it's a governed proof of work system. So, and this is actually where you need the machine learning also to stabilize the system. And this is not always needed. But if you have, for example, tacting times in the industrial production, as in Mercedes, you actually have just 2 seconds, for example, to actually where you need to verify that this transaction is actually true. So you optimize your system and your network exactly to handle those 2 seconds. And as I said, we have different blockchain networks that communicate to each other. So to optimize this, we don't put like one blockchain system for the entire automobile manufacturer. That doesn't make sense. So you have, for example, one blockchain system in one production line communicating to another production line to exactly face this. But of course, there are always trade-offs. If you lower down the blockchain size, of course there is a higher possibility actually to attack the system. So it's not really small, but it's not really across different factories, and it should be more costly actually to attack the system than you gain from it. Yes.
Yeah, maybe a similar question or follow-up. So my question would have been, how can you trust the blockchain if everybody sets up his own blockchain?
Well, this is as such a question when of course the automobile manufacturer as such has not the incentive to actually cheat on the system. It is more individual people who have an incentive to cheat on the system, and they of course can't just set up a new blockchain network. And this network is really optimized for the corporation and for a specific use case, and of course to handle insider attacks. Sorry, yes.
Between all the miners.
Yes.
Take much more time than grow.
If you mean like if the network is larger, so and it takes more time because of the network latency? Yeah, but then you don't have the requirement, for example, for 2 seconds. This is really, for example, for certain production lines or just a certain factory, you have a local network. As such, if you would communicate, for example, between the factory in Marienfelde and Stuttgart, this is of course seconds as a tactic time. You have, and of course you need to increase that. And this is always a trade-off and such. And this is, I mean, this is more for really, this is for supporting systems. This is not to replace anything. This is to enable, for example, auditing, to have a trusted infrastructure, and you don't put every information on a blockchain. I mean, this is not, some people do that, but it's, I don't think that's how it should be done. No? Yes.
How do you optimize the shell size when you drop dynamically grow as a factory, and then after a year you say, okay, it's scaling out and the block needs to be bigger, and then this is dynamic. Actually, some way to do this dynamically, or
Yes, this is actually dynamically. I mean, there is now also we cooperate with Ethereum, so we have the Ethereum Enterprise solution where you can actually also manipulate basically those properties in the system. So we have some. I mean, the problem is always if you have such private networks, you need to also keep up with open source developments. In this way, Ethereum is also developed in this way that you have this open source development. You can take this open source development and you build your own engines. And these engines are, for example, this base network to modify the system, modify the properties specifically for your use case.
Thank you so much. Round of applause.